and welcome to number 3 of this acid and base series. In the previous 2 we've looked at ways of calculating the pHs of strong acids and also looked at some of the nomenclature around acid-base equilibrium. In this one we're going to start to look at the ability to calculate the pH of an alkali or a basic solution. So if we had, for example, a potassium hydroxide solution whereby the concentration was 0.1 moles per litre, we know from the previous clip that the pH is defined as the minus log base 10 of the H plus ion concentration. In a potassium hydroxide solution, we are not going to have any H plus ions, so it's going to be very difficult to calculate the subsequent pH. However, water has a strange property whereby it can itself dissociate into hydrogen ions and hydroxide ions. Now, it doesn't do this to a large amount, it's a fairly tiny fraction. However, we have this situation where this tiny fraction of water molecules are constantly dissociating into their ions when we are in an equilibrium. And importantly, for potassium hydroxide and HCl and all acid-based solutions, we're in water. And so this equilibrium will be also present in that situation. The equilibrium will have an equilibrium constant, a K, and for water, because of the relative sizes of the concentrations, the Kw, so the ionic product of water, and an equilibrium constant, the W representing the water, the Kw is defined as the product of H plus multiplied by the OH minus ions. In normal equilibrium constants, we would obviously have a water term on the bottom of this equilibrium constant, but because water is a much greater concentration and the amount of dissociation that happens is actually quite low, we can, for the numerical purposes of this, ignore the water concentration because it's relatively large, relatively constant, and so we can incorporate it into the constant, and to all intents and purposes, for what we need, we ignore it. And it is defined as, in this situation, Kw is 1 times 10 to the minus 14 with units of moles squared per decimeter to the minus 6. Now, in this situation, what we can now do, therefore, if we were thinking about our potassium hydroxide solution at the start of this clip, we can establish that the H plus ion concentration, by simple rearrangement of the equation, is equal to Kw divided by the OH minus ion concentration. And if we know that Kw at 298 Kelvin is 1 times 10 to the minus 14, and we know that our potassium hydroxide, being a strong base, will completely dissociate to give 0.1 moles per litre of hydroxide ions, that allows us to evaluate that the H plus ion concentration equal to 1 times 10 to the minus 13. So this will give us the concentration now of the H plus ions. Because we're in aqueous solution and we've added some hydroxide, the equilibriums will all disturb and produce 1 times 10 to the minus 13 moles per litre of H plus ions. This can then be placed into the pH equation, the minus log base 10 of the H plus ion concentration, and this would subsequently give us a pH of 13, which is quite reasonable for a strong alkali. Now, what is also interesting about this equilibrium is that as water dissociates into H plus ions and hydroxide ions, that forward reaction is going to be endothermic, which means it's going to be temperature dependent. Now, if we were to increase the temperature of the potassium hydroxide solution, now I mentioned very briefly earlier that this was at 298 Kelvin. So if we were to increase the temperature of the potassium hydroxide solution that we have got, the equilibrium will move and attempt to counteract that increase in temperature and will actually go towards the side of products. We'll get more dissociation. This will mean we will get an increasing amount of hydrogen ions. Now, if we get an increasing amount of hydrogen ions, assuming that at room temperature the pH of water is 7, it's possible that if we increase the temperature of water, we will increase the concentration of hydroxide ions and actually see the pH fall. Now, this may be a weird phenomenon to what you've experienced in lower school years, but this means that the only point at which the pH of water is neutral at pH 7 is at 298 Kelvin. At temperatures which are greater than 298 Kelvin, the pH will be lower than 7. And so it means that we're going to change the pH of water just by changing its temperature. However, because we are doing a dissociation, and so H plus and OH minus will always be the same in the dissociation of water, then the solution will still remain neutral, in the sense that the number of hydrogen ions is exactly counteracted by the number of hydroxide ions. Neutral solutions simply mean that. They don't necessarily mean that they are at pH 7. It is possible to have a solution with a pH of lower than 7, but it still be neutral, whereby the H plus ion equals the hydroxide ions. And so the ionic product of water is a very important equation and an important equilibrium, because it allows us to understand the dissociation of water and ultimately its temperature dependence on its equilibrium. But also it allows us to calculate the pH of strong bases, because if we were to, as we did in the previous question, if we were to rearrange the Kw, just in summary, knowing the concentration of the strong alkali, the strong base, we can calculate the H plus ion concentration and subsequently calculate the pH. Similarly to acids, when we did strong acids, if you have a substance which would generate 2 hydroxides or multiple hydroxides, obviously take that into account in your concentration equation as well when you're deriving that value to put into the equation. But using Kw allows us to relate H plus ions to hydroxide ions and subsequently give us pH calculations for strong bases. What we will do in the next few clips is we will move on to weak acids this time, whereby we will look at their equilibrium. It's not strictly as simple as we've said as putting numbers into the equation, but we'll have a look at weak acids in the next one. So I'll see you in there. Thank you very much.